And the next presenter, I think that we will stay on topic, Professor Nikiforchin. So, Professor Nikiforchin is from Ukraine, and it will be something similar with John
Thank you.
Gabetta. Please.
Thank you. And dear colleagues, my talk about development of new methodological approach for an evaluation of degradation of pipeline steels in service degradation based on a measurement of electrochemical properties of fracture surface, not as usual typical polished metal, but fracture surface. Here? Oh. Why? Opa. Okay. Okay. It is nowadays that the integrity of pipeline gas transit pipe network is very big problem due agent of steels, and important role belongs it hydrogen, because transported hydrocarbons serve as a source of hydrogenation of pipe wall from internal side, and this is from internal side here. Where is point? No. Why? Oh, from internal side. And it is caused simultaneous effect of hydrogen and stresses, promotes formation of damaging on nano and micro scales, and finally the degradation of mechanical properties, first of all brittle fracture resistance characteristics. And here you can see on the left figure degrees of impact strength during service up to 40 years of gas pipeline, and you can see very sharp degrees, and on right figure you can see additionally strong degrees of fracture toughness by J integral, critical levels of J integral. You can see in both cases this characteristic of brittle correction degrees in 5 times in comparison with as received state. It is very brittle behavior of material. And in previous work, we proposed to use electrochemical measurement for an evaluation of mechanical properties of in-surface degraded steels, because some electrochemical properties are sensitive to aging of materials. Yes, and for example, on right side, you can see, for example, change of polarization resistance. It is electrochemical characteristic, and from other hand, change of impact strength. If you can measure in field conditions electrochemical properties, you can predict in some way if, impact stress without mechanical tests. It is the base for non-destructive evaluation or prediction of current mechanical properties. Yes, if you can measure in field conditions electrochemical properties. In this work, we propose to use not electrochemical properties on polished metal, but fracture surface. Why? It is known that the process of degradation occurs non-uniformly, but therefore fracture crack propagates via local sites with minimum energy for fracture. It means maximum level of degradation. So we expect that fracture surface concentrate is the most measured changes if metal which led to fracture, brittle fracture. it is philosophy of our approach to measure electrochemical properties of fracture surface of specimens after brittle fracture resistance test, for example, impact strength, as in this work. So, from one hand, we used the pipeline steel C52 in as-received state and 2 variants after 30 years of operation. And from another side, a row of steels, carbon steels with different content of carbon from 0.2 to 1.2% of carbons. Why we do test these carbon steels? We used the theory of Russian scientists Suviljev and Nechayev. They theory intergranular stress corrosion cracking in gas propellant steel is caused by formation on grain boundary very thin of nano-size thickness carbide, and for such formation of carbide is enough free carbon closer to grain boundary only 1 micron. This short distance is enough for diffusion during ambient temperature during, for example, 20, 30, 50 years. And in such a way, he explained brittle fracture behavior, transgranular brittle fracture behavior after a long term of operation. We suppose the same process can be inside in grain if only 1 micron is enough for formation of carbide, which cause brittle fracture, and in such a way to explain also transgranular brittle fracture during service. On left, you can see for as-received state ductile behavior of metal, and on the right, after operation, you have brittle, typical transgranular brittle fracture, and brittle fracture. But this, to our opinion, this brittle fracture behavior is caused by enrichment of fracture surface by carbides. It means surface is enriched by carbon, by carbides on fracture. But it is known that carbides are very sensitive to are very electrochemical sensitive. It means that measure of electrochemical properties of surface enriched by carbide, we should detect this enrichment of carbon on surface. And in such a way to confirm this approach that carbide formation is responsible only for transgranular fracture. We measure electrochemical, as electrochemical properties, we use only potential, corrosion potential. The most simple for measurement, we doesn't need to know area, real area of fracture. And it allows for a row of steels with different content of carbon to build line, as calibration line, dependence of potential on content of carbon. Lower points correspond potential of fracture softness for exploited steel. And you can see if extrapolate this point to this calibration line, you can see that carbon content on fracture surface, we expect, if to believe this approach, about 2% of carbon, in order more than average percent, 0.2 for these steels. So, and we measure, compare potential for polished metal is usually, and fracture surface for steels, pipeline steels for as-received state and after service. And it allows to build, there you can see the most important results. If we compare potential for as-received state we do not observe essential differences. But we compare for exploited steels, you can see big difference between potential for polished metal, typical potential, and for measured on fracture surface. On right figure, you can see impact strength for such state of materials. High level for S-receive state, and low levels is approximately in 3 times lower for exploited metal. If for more abrasive metal, we obtain more difference between potential for polished metal and for potential for on fracture surface.
5 minutes.
Okay. And if we back to this calibration line, we can see that materials with lower level of impact strength and lower level, more shifted in negative direction corrosion potential. For such material, content of carbon is more than 1%. And for materials less degraded, this carbon is about 1.5%. It means that we have correlation from one side, impact strength, shift of electrode potential measured on fracture surface. Of course, this method allows to predict such great level if we suppose that only this factor of carbide formation is responsible for material degradation. It is very important to show that for S-receive state, difference between potentials is small. It means that fracture surface with great deformed material, ductile behavior of such case, does not affect so strong effect for potential as for aged materials. For aged materials, level of plastic deformation is less. This is factor effect of plastic deformation on several odd shift of materials is, to our opinion, is negligible in comparison with effect of change of state of materials. To our opinion, is due formation of hydrogen of carbides of carbon. So it is. You can see the conclusions remarks, and additionally, I would like to add that it is only the first step. We use very simple parameters of electrochemical parameters. It is corrosion potential. To our experience, polarization resistance, corrosion current are the most sensitive to material degradation than potential. However, in this case, we need to calculate real area of fracture surface and calculate real density of, for example, corrosion current. And it is possible, and we expect that when we use another electrochemical parameter more sensitive to material degradation, we should get more difference, these parameters will be more sensitive parameters. This measured on fracture surface will be, to our opinion, more sensitive than potential. Thank you very much for your attention.
Please, questions? Okay, I will have one additional question. This presentation and previous presentation is very interesting because it's talk about a long-term hydrogenation of real components in exploitation, and these results in Ukraine related to more than 30 years of exploitation is very rare and also valuable because they revealed some new mechanisms of effects of hydrogen on pipelines during a long-term exploitation. In your conclusions, you briefly give us some summary about the, let's say, hydrogen damage mechanism after long-term hydrogenation after 30 years. I'm interested a little bit more about the effects on carbon content and also general effects of hydrogen after such a long exploitation of pipelines. What's the mechanism? Because it's very complex. We see that we have a decline in impact strength. And what's the real reason for that, from your point of view?
No. It is known that, for example, high carbon steels are more sensitive to hydrogen embrittlement than low carbon steels. Yes. Therefore, if we have in local places enrichment by carbon carbide, we expect that when we will have hydrogenation of metal, we expect in these places damage. These factors are in combination. We have absolutely direct confirmation role of hydrogen. For example, for oil pipeline steel, upper part of pipe and lower part of pipe. Lower part of pipe is very brittle, where deposited water, yes, from oil serve a source of hydrogen. Yes, and for example, for oil storage, lower part of oil storage where water is gathered, yes, on bottom of oil storage, this material of oil storage is very embrittlement, is very because of effect of hydrogen. Corrosion is only source of hydrogenation. Thank you.
Thank you. Thank you very much.